It says it's live. I believe it. It hasn't shown up on YouTube yet. Okay, refreshing. Yes, okay. We are actually live. I have confirmed it. Okay. And I closed the window that has your full name in it. I will get that back.
I know it if you need it.
That's just awkward. And maybe called for. No, I got it. Okay. Hello, everyone, and welcome to this, the 11th Center for Lunar Science and Exploration Hangout. We are coming to you each month, roughly the third Wednesday of each month, to talk about all the things that NASA's Survey Network is doing to work to explore all the minor bodies across our solar system, from the moon to the asteroids and a few random objects in between and beyond. And it's the beyond we're going to be talking about today. We have with us Dr. Tracy Becker, who is a planetary scientist at the Southwest Research Institute in San Antonio, Texas. And she's part of the exciting and newly announced Europa Clipper mission. But before we start talking to her, I'd like to say we have Andy Shaner, my co-host, with us, who is getting ready to be at the Lunar and Planetary Sciences Conference down in Texas, other side of Texas, down in the Woodlands, which is north side of Houston, next week. Do you have anything that you want to let people know about as we gear up for the big science event next week?
Well, it'll certainly be that. I mean, this is the big annual conference. We bring in planetary scientists from the country and from around the world, too, to this meeting. Everything from the moon to Mars to satellites, outer planets to Pluto, asteroids, even solar system formation. We've got it all. So it should be a pretty exciting week.
So everyone stay tuned on Twitter and on the social medias. Hashtag is probably going to be LPSC 2017. And people will be tweeting out the meeting with their little micro blogger badges. It's a really good conference for giving us access. I won't be there this year, but I, like you in the audience, will be following along online. Now, Tracy, you are part of some of the most exciting science going on right now. It is so exciting for me to have you here. Welcome. Can you tell the audience a little bit about what you've been up to?
Thanks. It's so fun to be here. I've been very fortunate in getting involved in some of the coolest science missions that are going on. For the last 6 years, I got to work on data from the Cassini spacecraft, which is currently in orbit around Saturn. And I was studying the rings of Saturn, which is just naturally awesome, of course. So I got to do that for a while. And now my focus is actually on Europa, which is one of the moons of Jupiter. And it's kind of the target of the next big NASA mission, which is the Europa Clipper mission, which will be heading out there. Hopefully 2020 it'll launch, in 2022, and it'll be there not too long after that. So we can get to see all the amazing things that there's going to be to see at Europa.
Now, speaking of Saturn's rings, I think everyone who is part of the planetary science community and well beyond the planetary science community took note of the ravioli in space last week. This is Saturn's moon Pan. Can you tell us a little bit about this? And I'm going to try and pull up a picture to show the audience.
It was a phenomenal picture, but like everyone else, I kind of just was a witness when that got posted. But it's this small moon that's actually inside the ring system. So the rings extend pretty far out from Saturn, and there are these gaps that are maintained by these small ring moons. This is one of the bigger ones of those. It's called Pan, and it keeps open this inky gap, which is a couple hundred kilometers across. The moon itself is only like 30 kilometers across. But it is insane because we've never seen an image of that moon at that resolution where we could see the shape that is just so crazy. And I'm not a moon scientist to really know about what exactly is going on there, but you can tell that the pull from Saturn and maybe some of the rings on the sides are coming and basically filling out the equator of the moon. So I'm just as excited as everyone else to figure out what the heck is going on with this moon. It's incredible. I was showing pictures of people, just strangers on an airplane that I was on when I saw this picture for the first time. I was like, look at this moon, it's crazy.
So what's kind of crazy about it is it has these crisscrossing crack features, this equatorial belt, layer of pasta. And this is something we've never seen before. And it sounds like people are starting to theorize this might be collisions with debris in the rings that are building this up around the equator.
I think that would be my first natural thought as to what that is. I'm still waiting to hear what everyone else kind of really has to say about it. But yeah, we do see on some of these other moons too, we see some equatorial ridges on some of the Saturnian moons, but nothing like this, where the extent of that skirt, that equatorial ridge, is just so extreme compared to the size of the body of the moon. But yeah, I would say it's a natural assumption to assume something with the particles actually accreting around the equator might be happening there.
And to give people a perspective, here is Pan in its natural habitat. The stripe going across the rings, that's actually a shadow being cast by Pan across the rings with the sun coming in at a steep angle. Can you explain beyond the shadow what all we're seeing here?
Yeah, so this is Saturn's A ring, which is the outermost part of the main ring system. And that gap right there, so you see the yellow, that's all the reflected light from the rings, and that black space is actually a true gap that's maintained by the gravity of the moon itself. In this picture, you can't see it quite so well, but in some of these images, you can really see these waves on either side of the ring edges caused by the moon's influence, its gravitational influence. As it kind of goes by, it creates these wakes the same way like a boat would. Just its influence on those ring particles. So yeah, I mean, this gap is it's not a huge gap. Like I said, it's a couple hundred kilometers, so it's not small. It's definitely visible from all of the images that you can see. But the moon is just this tiny little 35-kilometer sized moon that's maintaining this awesome gap, and it really kind of lends itself. A lot of people like to say that Saturn's rings are a laboratory for planet formation, because we can see accretion, we can see what's happening with particles as they kind of can clump together, and you get these moons and stuff. So you can really make analogies to how solar systems originally formed by looking at what the processes going on are, that are going on in the rings.
So it's just kind of amazing that we're just now getting this incredible image of the moon. What was it that allowed us to get to this point?
Yeah, so Cassini has been hanging out around Saturn for almost 13 years. So it's had a very long lifetime and an awesome mission. We've gotten so much information from it about Saturn, about the rings, about all the moons. But now it's coming to an end. So we're going to crash Cassini into Saturn at the end of its lifetime, basically this year in September. And so they're doing some pretty crazy new trajectories and new orbits where they're really going in and out of the ring plane, kind of crossing through the ring plane. So you can get these super close up images that they never were able to get before. They're getting, now that it's kind of the end of the mission, you can do some of these trajectories that were maybe considered to be a little bit more nerve-wracking for the NASA scientists, because you don't want it to hit a particle, or anything that could disrupt the actual spacecraft. But now that it's the end, it's doing these awesome, amazing orbits where it's really going to constrain the mass of the rings, which is something that we really, really want to know about. And then also just a super awesome photo op for all of the moons and the rings.
And these past couple of years, we've been getting all sorts of new high-risk behaviors out of the mission because they've been able to extend it far beyond what anyone had ever initially expected. Now, you had to recognize at a certain point, Cassini will end. We just know this. And you've moved out into other icy bodies, and you made the jump from the moons of Saturn and the rings of Saturn out to the world that does not belong to us, Europa. What lured you from ringed Saturn to icy Europa? And I'm going to bring up my personal favorite picture of Europa while you talk.
Well, the most basic answer is I graduated from the work that I was doing was for my Ph.D. when I was studying Saturn's rings, and then I had to get a job. So that's the most direct answer. But the real answer too is that Europa is awesome. I mean, it is one of the coolest bodies in the solar system. Not just literally cold water ice, but it's just a fascinating place. And like I said, I've just been so lucky that I get to be involved now in this mission to go there and see everything we're going to learn there in some time. We've got a lot of time till we get there, but it's really cool actually. Working on Cassini, I started, only a few years ago. The mission had been alive and well and running perfectly for a decade essentially, and now I get to see the inner workings of how a mission really gets started. So I get to see all the planning that goes into it and all of the details and nuances and really the whole thought out process that all of the people who have already started it and proposed it and been working on it for the last few years really had their vision and stuff. And I'm happy to get to help them kind of put that vision together and see what we're going to get when we get there.
And one of the things that makes science so awesome is the same physics that applies to Pan, that applies to all of the moons of Saturn, also applies, well, to all the moons. It's just a matter of what we see varies with composition, varies with the gravity interactions and all of these other things, but it's the same underlying science. What are some of the questions that you got studying Saturn that now you're hoping to be able to carry out and answer with Europa?
That's a good question. So one of the things, besides just studying icy stuff, my kind of expertise is using ultraviolet light to study those things. And so I worked on Cassini. I was working on the UVIS instrument, which is the ultraviolet imaging spectrograph. And now I'm helping out with the team that's working on the UV instrument that's going to Europa Clipper, the Europa UVS instrument. And so so there are a lot of things that you can apply from what we did, even though it was rings, to what we're going to do with the moon. And that's looking at the spectra, understanding kind of what compositions you're going to see, what those fingerprints are in the UV wavelengths. One of the main things that I used to do a lot with the rings that I'm really going to apply to this moon is a thing that we call stellar occultation. So it's a technique where we actually watch a star go behind the object of interest, and we study what happens to that starlight as that happens. So when it happens with the rings, you see all this flickering of light, essentially. You see a bright star, then it goes behind the rings, and that signal dips down because the ring particles are blocking it. You can say something about the particle sizes and how well they're packed together based on how much that light decreases. With Europa, one of the things we'll do is look for the tenuous atmosphere. And so you can study what the star spectrum looks like, so what that starlight looks like at different wavelengths. And as it goes behind the atmosphere, you can kind of pull out what's making up that atmosphere, what kind of gases are there, based on what wavelengths of light, what energy of light gets absorbed as the star passes behind that atmosphere.
I was going to ask you a question, but maybe the answer to this will come from those experiments. Is where is this tenuous atmosphere? What's producing it? What's going on the surface to produce it?
That's a great question. So it's a few things, but generally it's the bombardment of the surface itself. It's a very tenuous atmosphere that's really created by micrometeorite impacts onto the surface, or the radiation impact from Jupiter's intense magnetic field that really kick up some of these constituents that can form this kind of very thin atmosphere that's there.
So we have an audience out there live who's interested in asking some questions. And the question that we just got was, are Pan and the rings orbiting at different speeds?
Yeah, that's a good question. So everything is orbiting based on how far out from Saturn it is. So everything is at its own speed. It's kind of like a race car around the track. Like if you're closer to Saturn, you're going to be orbiting faster. If you're further from Saturn, you're going to be orbiting more slowly. So yeah, so when you see, one of the cool things is if you look at some of those images of what I was describing, those wakes that kind of ripple in the rings that you can see because of Pan, you can see that some of those ripples are actually ahead of Pan, or it looks like it's ahead of it. But it's because those particles are moving faster than the moon. So they got to see the moon and then they've moved on. So they have the effect of the moon. They look like it's in front of the moon. Really, it's just because it's beating the moon, because the moon's a little bit further out. So those particles ran by, got disturbed, and then kept going. Whereas, and then the particles outside of the Inky gap will have those, will look like it's behind what you kind of expect. Yeah, those are cool.
and again, the black on this is caused from the shadows. So you can see that these waves are actually raised up above the normal plane of the rings.
Yeah. And that one, I think that one is actually, that one might actually be Daphnis.
Okay, sorry.
No, that's okay. It's the exact same principle though. And that gap is a little bit thinner. The moon's a little bit smaller, and it's just outside of where the Inky gap is. So it's a little bit further from the center of Saturn. But they're quite close together actually, and they're really cool spots to understand what's going on in the rings.
So, back to Europa. With the Europa Clipper, this is a mission you're going to be waiting for years to get data from. So what are the things that you do ahead of your spacecraft getting to the world? It's not a planet. Europa's a icy moon. It's its own world. What are some of the things that you're doing to prepare for the onslaught of data that will be coming in many years?
Yeah, that's a great question. So I'm working with the PI of the instrument that I'm working with, the UV instrument. His name is Kurt Rutherford, and we are basically, and the team that he has assembled, we're working on really kind of figuring out some of the crazy details of exactly what do we want to look at. With the occultations I was talking about, we're finding which stars are going to be the good opportunities to see that happen. We are trying to figure out how much data volume we're going to use, how much, basically how much power we have to really see these observations and have enough room to send it all back to Earth and actually learn anything from it. We're planning out kind of what we're hoping to see, how many, the overall team, the overall spacecraft team is planning out how those flybys are going to happen, what the trajectory is going to look like. With Europa, we're going to be actually with Clipper, it's going to be orbiting Jupiter. And it's just going to do a bunch of passes by Europa, really close by, some of them, so that we can learn a lot about the moon. But we're not going to orbit Europa itself. We're going to use Jupiter as our kind of orbit center, and then just do these close flybys of the moon to really see what we learn about. So we have to figure out the trajectories and where is the spacecraft going to look? Are we going to get coverage of the entire moon, or would we only end up just seeing one part of it? Obviously, we want to see as much as we can see. So it's kind of all those details on the spacecraft side, and on the instrument side, we're really trying to figure out what observations are going to give us the optimal science return so that we can learn as much as we can.
Now, Europa presents a whole lot of challenges for a mission like this. So first of all, like you said, you aren't going to be orbiting the moon. And there's a lot of both energy reasons and safety reasons for Europa that you're not doing this. Can you explain some of the reasons that you're not going to orbit? Because I know everyone's like, what do you mean you're not orbiting?
I think one of the main reasons is that the radiation environment due to Jupiter is really, really intense. And so if you just hang out there, all of your instruments are going to get fried pretty quick. And so you won't get the return that you're trying to get. So we do these close flybys where we kind of enter that radiation environment and then we get out of it. And then, then we can do our calibrations and send the data back. And it works out nicely because there'll be flybys of the other moons as well. There's not necessarily any science going to be done there, but maybe in the extended mission. And so we can really see the trajectory kind of gives us time to send everything back, I think, without frying all of our instruments before we really get everything we want to get. So it really does extend the lifetime of the mission so that we can see everything.
Are there any estimates on how, like what percentage of the surface you may be able to image?
The goal is like 87. It's high. We're going to see most of the surface, and it really depends on the instrument too. Some of the instruments have kind of bigger fields of view, higher resolution or lower resolution. So it will depend on the instrument, because we have a few instruments. There's some imagers that are in the visible. The one that I said I'm working on is a UV imager. So they all have different kinds of sizes. But some of the observations, we're going to just look at the whole hemisphere from far away. And then as you get closer, you're going to get, you know, really high resolution, but kind of smaller pieces. So it'll be a combination of resolutions, and but we will really see almost all of the surface.
Now, there are challenges to trying to get the entire surface that makes it not as easy as it might be with some of the other worlds in our solar system. What are some of the things that make it so hard for you to get the entire surface?
Well, I guess part of it is a tidally locked moon.
Yeah.
So you do have to fly the spacecraft in different kind of routes. You're gonna have to fly above it and below it if we want to see the poles. You're gonna have to fly outside of it, and I guess inside of it to get the side that's always facing Jupiter. So yeah, there's challenges there, and the people working on that, they're doing an awesome job, I think, because I think they really are gonna get as much coverage as we possibly can.
So this is definitely one of those situations where there's going to be a lot of maneuvering of your spacecraft going on.
Yeah, the plan would be to have it way early out, though, so that there's not too much happening in real time. They have kind of the plan already formulating now, so that the spacecraft will know what to do well in advance.
So we have a question coming in from the audience. Will there be a focus on the South Polar region? That seems to be a very interesting area.
So that's an awesome question. We've seen a couple things now. So with Enceladus, which is one of the moons of Saturn, it was at the South Pole where we saw plumes, water plumes coming out of the moon, which is an awesome thing to see, because that means we're really seeing interaction. We're really being able to see what's going on underneath the surface of Enceladus with that. So the goal will certainly be to find these plumes on Europa. They've been tentatively detected before with Hubble. So the Hubble Space Telescope a couple years ago saw the aurora basically created from an H2O plume. And more recently, there was another detection where Europa was going in front of Jupiter, and they could see this little kind of blurb off the side that was absorbing some of the light coming from Jupiter. So there's been these two kind of different detections of it, but they really are pushing the limits of those instruments. So it really will be when we get out there that we can really find those plumes and really understand what's going on with them. And they did, as the person asked, it was the two detections were kind of in the southern region, not exactly at the South Pole, so it's not exactly the same as Enceladus, but that's certainly, I think, where people are going to keep looking first. But yeah, it'll be if we are there and we can see those plumes, that is one of the greatest ways we can say that we understand what's going on underneath the surface, what the constituents are of the ocean that's underneath.
And here's the HST observations where you can see they were doing images of a specific molecule. These are molecules when they get observed, and again, like you said, it's the South Pole where they're seeing off the edge of the world this extra abundance of the volatiles escaping.
Right.
So you guys are gearing up to do this. It sounds like there's folks doing all the observations they can do from here. And I know one of the reasons a lot of us are so excited about Europa is it does appear to have this dynamic ocean. What capacity is Europa Clipper going to have to give us new insights into this potential ocean?
So we have, on that mission, there are, I think, 9 instruments. 3, 6, yeah, I think 9 instruments that all have different but kind of synergistic capabilities. And so, as I keep talking about, I'm on the UV instrument, which we're really going to be focused on as looking. So that image that you just showed from Hubble, that was in UV wavelengths. And so UV, we're equipped to really look at those plumes, see that abundance of hydrogen, oxygen, and determine if there's really water plumes coming off, and we'll be much higher resolution, much closer, so you can actually see the plumes and everything. In the UV light, we'll also be looking at the surface, taking images, and really trying to figure out what the constituents are that are on the surface of Europa. There's also visible cameras that will do very similar things, but at different wavelengths. And so you can really learn different things at different wavelengths. Because as I said earlier, the different compounds, the different constituents of the surface have kind of their spectral fingerprint at different wavelengths. So sometimes it's ambiguous if you just see a certain feature in the visible. Sometimes the UV will help you verify that that's what you think it really is. It really is sulfur. It really is oxygen. So you can do that with UV and visible light synergistically. There's also an infrared detector, so and thermal, so they'll be able to see kind of warm spots the same way that we do have on Enceladus, where you can see that there's actually a hot spot right where those Enceladus plumes are. And there are instruments there's a radar instrument, so you can kind of see down into the water, see into the thickness of the ice shell. There are instruments that'll do in situ measurements, where they'll actually scoop up parts of the atmosphere and analyze the constituents that way. So there's kind of a huge broad base of different instruments that'll all work together to really kind of nail down the main goal of the mission, which really is to assess the habitability of Europa, see if there really is a chance that there could be something underneath the surface that's alive.
So the question that everyone's going to be asking is, will the instrument that allows you to sample anything from plumes if you time and everything is just right, will it be able to look for organics?
I think it will. I'm not involved in that particular instrument, but I do think it will be able to assess some things about organics, and that doesn't necessarily mean it detects life, but it detects
building blocks.
It detects building blocks, yeah. So we'll do that, and then there's a number of different building blocks where if they all come together just right, maybe there's something that could be said about the chances that there are. But this mission really is to assess the habitability. So what is the salinity of the ocean that's underneath, and what is the temperature, so that we can really say, is this something that life as we sort of know it at least has the potential of being there, or is it just really, really absurd and unreasonable to assume that there's anything there?
It's all amazingly exciting, and you are demonstrating how people in the space sciences really have to be experts at delayed gratification. How long is it before you can expect first data?
So it depends on a couple different things, when it launches exactly and by what means it launches. But the kind of current plan is for it to arrive in 2026. So yeah, it's a while, a little less than a decade.
And this is how we measure the stages of our life. Which mission am I getting data from right now?
Yep.
Other people have other means. We have spacecraft. So this half hour has absolutely flown. Are there any parting words that you'd like to leave our audience with?
Stay tuned. I mean, there's always lots of cool stuff. So I've been fortunate to work on Cassini and now on the Clipper, but there's Juno going on right now. There's OSIRIS-REx heading to an asteroid. There's always something really cool going on. So just stay tuned and you'll find something awesome to learn more about our solar system that we didn't know yesterday.
That's entirely true. And for any of you out there who want to get involved in helping do NASA science today, go check out cosmoquest.org, where we're working with these missions. When OSIRIS-REx gets to Bennu, we'll be out there helping them find the rocks. And right now we're helping map out the Moon, Mercury, Mars, and Vesta. And Andy, how can people get involved with other things related to SURVEY and the Center for Lunar Science and Exploration?
Well, this is quite possibly one of the best and most efficient ways is by taking part in our monthly webinars. Our next one is on April, look at my calendar here, April 19th, and that's with Dr. Jennifer Heldman out at NASA Ames. She's the PI for the Finesse survey team. So she'll be talking about the science and exploration and the education that their team does out in the field.
So hit subscribe on YouTube if you're out there watching live. And if you're watching later, well, hit subscribe so that you'll get that YouTube notification to let you know next time we launch one of these events. Now, the last and most important question is, Tracy, where can people follow up on what you're doing?
There is a website for SWRI, the Southwest Research Institute. You can always check out stuff going on there. There's the best way to really see what's going on with NASA is just going to nasa.gov, and you can type in Europa Clipper and see what's the update status for that. Following Cassini right now is a big thing. As I said, in a few months there will be no more Cassini, so follow it as it ends. My Twitter handle, I don't tweet very often, but maybe if I get some new followers, I'd tweet a lot more. It's at tbecca, so TBECKAA, at gmail.com, or well, at gmail.com if you want to email me, or tbecca, just my Twitter handle. There's also, I'll do a shout out, there's some good podcasts out there that I'm sometimes on. I haven't been on lately, but there's one called Walk About the Galaxy. That's one that I used to work on a lot at UCF, and there's some cool scientists there that are still working on Cassini. Josh Caldwell handles that one, and so you can learn all about Cassini as it kind of comes to an end through that podcast.
So this has been absolutely great. Thank you for joining us, everyone, and we will see you next month. And have a great morning, afternoon, or evening, wherever you may be in the world.